Okay. So let us start with the revision of electrochemistry. So as you all know, electrochemistry involves electrochemical cell, otherwise called as galvanic or voltaic cell, which is going to convert chemical reaction to electrical reaction. By how, which is the driving force for this conversion is, it should be a redox reaction. It converts chemical energy to electrical energy by means of energy obtained from spontaneous redox reaction. We are calling it as spontaneous redox because the reaction does not need any aid, it does not need any catalyst, not optimal condition, the reaction proceeds on its own. So that's why it is called as spontaneous redox. If it is happening in one container, then you are going to call it as direct spontaneous redox reaction. If it is happening in two different containers, then you call it as spontaneous indirect redox reaction. So the Daniel cell, which is given in the NCRT, is an example for electrochemical cell. All Daniel cells, say for example, zinc, copper, nickel, silver, chromium, lead, all these are example for Daniel cell, provided Daniel cell is an example for electrochemical cell. So the underlying principle under Daniel cell is indirect redox reaction happens. So you understood the concept very clearly. Left side, I'll be keeping a container with a rod dipped in electrolyte solution, and right side I have a container, a rod dipped in electrolyte solution. Both are different. So in left side, there will be oxidation happening. Say for example, zinc rod dipped in zinc sulfate solution, there is oxidation. So when oxidation happens, there is liberation of electron. These electrons will be traveling through the wire. They reach the container 2, where the electrons will be accepted by one more ion, so that ion will be reduced. But as the process keeps on continuing, the accumulated positive charge in the left hand side will prevent the outward movement of electrons. As a result, I'm just using a salt bridge to counteract this effect. Otherwise, I will be getting a potential which is going to oppose my cell potential. I don't want to happen. That's the reason why I'm using a salt bridge. So the main function of salt bridge, and you know what is the direction of current flow and electron flow. Electron flow is from negative to positive, and my current flow is opposite to that. And I will be calling these two separate cells as half cells. So half cell oxidation, half oxidation cell, half reduction cell. So always left side oxidation, anode negative charge. Then I think we saw what is the function of a salt bridge to maintain the electrical neutrality, to complete the circuit, to minimize the liquid junction potential. Then we saw what exactly my electrolyte should possess when it is acting in an electrochemical cell. So it should be inert, it should have, it should not be reacting with my electrode nor with my ions, and it should have good ionic mobility. Then we saw how to represent half cell equation, how to represent a cell equation. So based on that, we saw few numericals and how the salt bridge is represented. So we have seen a clue to indicate RP. So aqueous by salt side is, whenever you are seeing that case, then you can write it as RP. Then we saw what is electrode potential. So electrode potential is difference in potential between the electrode and its ions present in the electrolyte solution under equilibrium. This is called as electrode potential. Metals have a tendency to undergo oxidation as well as reduction, so they have a tendency to lose electron and accept electron. If oxidation occur, you call it as oxidation potential. If reduction occur, you call it as reduction potential. Then what is the use of inert electrode? My inert electrode should be conducting electricity, but it should not allow oxidation or reduction to happen. It should not allow the electron release nor accept the electron release. Then we saw how nature of metal, like its ion, concentration of ion, then temperature, all these are dependent on electrode potential. If you carry out this under standard conditions of temperature 298 degree Kelvin or 25 degrees Celsius, pressure as 1 atmosphere or 1 bar, provided the concentration of ion as 1 molar, then you can call electrode potential as standard electrode potential. I'm referring standard, so the condition was given and the results were taken. So your E naught value will be known to you. That will be given in the numericals. So you know electrode potential. Then you know standard electrode potential. You know what is oxidation potential. You know what is standard oxidation potential, reduction potential, standard reduction potential. In order to avoid confusion, our IUPAC has given us a clue to use SRP as SEP. So standard reduction potential is nothing but your standard electrode potential. And if you know standard reduction potential, your negative of SOP is your SRP. So if you know one value, you can write the other value by changing the convention of the sign. Then we moved to EMF of a cell. So what is EMF of a cell or E cell refers to difference in potential between two electrodes. So this is oxidation potential which is happening in anode plus reduction potential which is happening in the cathode. Together this is going to give me the EMF of a cell. So I derived an equation where I've got a final formula as EMF of cell is equal to electrode potential of cathode minus electrode potential of anode. Here there is no confusion since anode is given here, it does not indicate oxidation potential. Whenever I'm referring to EMF of cell, I'm referring to reduction potential of cathode minus reduction potential of anode. Children, whether I'm in the meeting, right? You people are hearing, listening,
Yes,
no?
ma'am.
Okay,
Yes, ma'am.
thank you. Then we saw few numericals based on standard cell potential. Say for example, in the numerical one, where they have given the E naught of nickel, E naught of silver, and they have asked me to find E naught of cell. So what is the formula for finding E naught of cell? E naught of cathode minus E naught of anode. All these are RP. But before solving the numerical, my first duty is I need to check whether SRP is given or SOP is given. So for that, I have a clue. Aqueous by S form is nothing but RP. So in this problem, both are RP, so I can directly solve it. If OP is given, then I need to change the convention and do. But always remember, left side oxidation happens, right side reduction happens. But you are going to represent reduction potential. You are not going to represent oxidation potential. Done. But you cannot expect in the numerical only RP will be directly given. They will also give OP. You need to convert it into RP. That's all. I think we have seen these many numericals. Then we saw what is the thermodynamic point of electrochemistry. What is referred as feasibility, which is nothing but spontaneity of a cell. How to relate Gibbs free energy. So Gibbs free energy delta G, if it is negative, then I mean to say some useful work is done by the system. Since we are dealing with the chapter electrochemistry, here useful work refers to electrical work. Here electrical work done by the system is considered to be useful. So if delta G is less than 0, if delta G is taking a value negative, then I'm going to call that reaction a spontaneous reaction. Then what is work done? Work done is equal to Q into delta V. What is Q is equal to? Charge of one electron into number of electrons. What is charge of one electron? Charge of one electron is equal to 1.67 into 10 power minus 19 coulombs. How many number of electrons are transferred in 1 mole of solution, which is nothing but n into Avogadro number. Then what is delta V? Delta V is nothing but your E naught of cell. So now I'm going to supply my Q value as well as my delta V value for W. So I know what is Q, charge of one electron into number of moles of electron. What is number of moles of electron? N into Avogadro number. What is delta V? Delta V is nothing but E of cell. So now when you substitute, you will be getting free energy changes minus NF E of cell. So what is this F? F is nothing but 1 Faraday, which is equal to 96,500 coulombs, which is nothing but charge present on 1 mole of electron. Okay, done. So for a spontaneous reaction, there are two criteria. Criteria number 1, my delta G value should be less than 0. My E naught of cell should be greater than 0. That's all. So you know now what is standard free energy change. Sorry, what is free energy change? Minus NF E naught of cell. What is standard free energy change means what the reaction has happened in standard condition. So what is delta G naught? It is nothing but minus NF E naught of cell. That's all. So we saw few numericals based on finding the free energy change and how to predict the spontaneity of the reaction. So for that, in order to find out delta G, you should know first what is E naught of cell. Only then you can find delta G, because what is the formula for delta G? Delta G is equal to minus N of E naught of cell. So I need to find first E naught of cell. So in the numerical, you will be getting the values of standard potential of zinc cell, then standard potential of copper cell value will be given. So use those values, check whether RP values are given. In this numerical which I am showing you, only RP was given because aqueous by solid form, so it is RP. I can directly supply it here to find out what is E naught of cell. Once I found out the E naught of cell, then I need to find delta G value. Find out whether delta G, whether you are getting negative or positive. Accordingly, you can write whether the reaction is feasible or not feasible. And what is the value of N? It is number of electrons transferred in the reaction. Few reactions you can get the value of N directly by seeing it. Say for the reaction zinc and copper, 2 electrons were transferred, so it's easy, a bit easy by seeing this. A few reaction, the number of electrons won't be same. For oxidation half, you'll be getting one number of electron, and for reduction half, you'll be getting different number of electron. So in order to make the electrons cancelling, you can multiply them with a integer so that the number of electrons will be common, and that number can be taken as n value. Is it clear, children, till here?
Yes, ma'am.
Yes, ma'am.
Thank you. Okay, then. Now I think we saw a problem number one with the nickel and hydrogen. Before knowing She, we have done this problem. So we know an outline of She. What is She? She is nothing but standard hydrogen electrode. It's a reference electrode, so whose potential is taken as 0 in order to find out the potential of another electron. So whenever I'm going to use She, then She can be used either as a cathode electrode or it can be used as an anode electrode. What is known, that can be kept. That I'll be explaining a bit later. So I think based on this, we saw numerical 1. This problem also based on that, whether the reaction is feasible or not feasible. Then we saw what is Nernst equation, which is used to find the EMF or electrode potential at any concentration at any temperature. So the equation which is used to find out, I mean, the which equation, Nernst equation, is used extensively in the numericals is this box. Electrode potential is equal to standard electrode potential minus 0.059. So you know how you got the 0.059, right? See, this 2.303 into our universal gas constant, whose value is 8.314 joules, into temperature 298 Kelvin. So when you give all those values, Faraday 96,500, if you give all the values, then you will be getting a number of 0.059 by N. So the first equation, the simplified version, is the second equation, which is used extensively in the numericals. So what is Nernst equation? It's used to find out the electrical potential of any cell at any concentration at any temperature. So what is the formula to calculate Nernst equation? Formula for Nernst equation: E is equal to E naught minus 0.059 by N, where N is nothing but number of electrons transferred, log 10, product concentration by reactant concentration. This is otherwise called as reaction quotient. Your P by R is otherwise called as reaction quotient. Okay. Now, based on this, we solved a few numericals. Here, if at all a pure solid is given, then you have to take that concentration as 1, which we have studied in class 11 states of matter. So in class 11 states of matter, while representing Kc and Kp, for pure solid concentration will be taken as unity. If it is aqueous, means what? If at all AQU is referred, if it is mentioned in the numerical, it means the solvent used there is pure water. So for pure water also, the solid mass or the concentration is taken as 1. So if you see pure solid or aqueous form where pure water is used, in those cases the concentration should be taken as unity. Okay. So based on this, we have dealt few numericals. Say for this problem we have done yesterday. Yes or no? You know, the previous one only we did, right? Which one we did? Number of, find the reduction and oxidation potential of iron. Fe2 plus, they have given the concentration, they have given 25 degrees Celsius, they have given the E naught value of Fe3 plus. Yeah, yesterday I did this problem, guess. We will do one more. Yeah, this one. This one also yesterday done, right? Minus 0.77 and plus 0.77. Yes, this is also yesterday done. We can do question number 3. Yeah, this one we can do now. Find the EMF of cell. They have given Cr by Cr3 plus. They have given zero point 0.1 molar. Iron, they have given 0.01 molar. 25 degrees Celsius is given. They have given the E naught of chromium. They have given the E naught of iron. Okay. These two values are given here. Now we need to find what we have to find. We have to find E naught of cell, right? Yeah. We have to find E naught of cell. E of cell. So what is E of cell is equal to E of cathode minus E of anode. All these are RPs, right? Now check the question whether RP was given. Yes, aqueous by solid. So chromium they have given RP. And what about the iron? Aqueous by solid. So this is also RP. So both the thing direct question. So directly they have given RP. No need to change the conversion. Just supply it in E of cathode minus E of anode. So they have given four values here, right? So you have to write ions Fe2 plus by Fe, that is minus 0.509 volt, minus of anode value, that is chromium's value they have given, that is minus 0.77. So I found E of cell. I have found E of cell. Children, I think you are getting the question. E naught of chromium, E naught of iron is given. And this is E of iron, E of chromium. Whether you are getting me right?
Yes, ma'am.
Yes. So this is E naught of chromium, this is E naught of iron. This is E of iron, this is E of chromium. That's what you can see the formula. I have written just E of cell is equal to E of cathode minus E of anode. I have done step 1. Step 2 is I need to supply it in Nernst equation. E of cell, electrode potential of cell at any concentration at any temperature is equal to standard E naught of cell minus 0.059 by n into log 10 product by reactant. I should know what is E naught of cell, right? I have found out E of cell. I have to find out what is E naught of cell. For that, I have to again go back to E naught of cell is equal to E naught of cathode minus E naught of anode. Now I have to supply this one, right? E naught of iron is minus 0.45 and E naught of chromium is minus 0.75. So I know now E naught. I know now E of cell. E naught of cell and E of cell is clear. So now what is the another factor which I need to know? I need to know what is N. So for the value of N, if I see the equation, chromium is giving 3 electrons while iron is giving 2 electrons. I have to make a common number. So I have multiplied equation 1 with 2 and equation 2 with 3. So I have got 6 electrons as common. So I have got my N value as 6. So I have got my N value as 6. Okay. So now N value is known, E naught of cell is known, E of cell is known, right? Now, before
Ma'am,
that,
I have a doubt.
yes, ma'am.
Ma'am, when you multiply 3 to the uh, Fe equation,
Hmm.
shouldn't it be 3 Fe, but you've written 2 Fe?
No, ma, 3 only. My handwriting is that one, my
No,
Karma.
ma'am, the right hand side.
Right hand side. Okay, here I have written wrong. Sorry, see, this is a mistake. Here I have corrected 3 Fe. Look at the down part where I have written the summary of the equation. I have summed up both the things, right? Whatever is left. Correct area you said 2 Cr giving rise to 2 Cr3 plus 3 2s are 6 electron. Equation 1 is correct. Equation 2 I have to multiply with a 3, right? Integer 3. So 3 Fe2 plus 6 electrons giving rise to 3 Fe. It should be 3 Fe, right? I have written 2 Fe here. It's a mistake I have done here. Now look at the sum up equation. 2 Cr plus 3 Fe2 plus gives 2 Cr3 plus 3 Fe. Here I have written 3 Fe. Fine, Arya?
Yes, ma'am.
Okay, done. Now, I have got a sum up equation. After cancelling the number of electrons, I have a sum up equation. I need to check for which product they have given me concentration. For which product concentration value is given in the numerical. Let me scroll up again. to show you. Look at the question they have given here. Cr3 plus concentration they have given as 0.1, and Fe2 plus concentration they have given 0.01. So they have given me the product for, they have given me the value of concentration of product Cr3 plus and Fe2 plus. So I know the value of Cr3 plus and Fe2 plus value is given from the numerical, so I'm going to use that. Got it, Arya?
Yes, ma'am.
Okay, so this one is solid now. Yes, this is solid because no charges. This is an ionic state for this 0.01, so 10 power minus 2. This also is given in the numerical, so 10 power minus 1. So this is also solid. So this is a clue given from the numerical. See, I have got a wholesome equation. In the wholesome equation, I don't know which has to come to product and which has to come to reactant, right? In order to avoid confusion, I have told you the concentration of solid will be taken as unity. So this 2Cr is nothing but 1. You should not consider this solid category. Pure solid is constant, it is unity. So don't take the solid. So in right hand side also you are able to see this solid. Fe is given as solid. So this is also solid. This should not, this is a constant. Its value should not be taken. So leave off this. So what else is remaining? Fe2 plus and Cr3 plus is remaining. I no need to break my head because the value is given in the numerical. So I have got all the values. I know what is E of cell. I know what is E naught of cell. I found out what is N. I know what is product. I know what is reactant. Now everything should be given now. So E of cell is equal to E naught of cell minus 0.59 by N value is 6, product by reactant. Now I have to just put it in Nernst equation and I will be getting an answer. The answer should be expressed in volts. The answer should be expressed in volts. Is it clear, children, this numerical to everyone?
Yes, ma'am.
Yes, ma'am.
So definitely you will be getting a chance to get EMF of cell in part C, in last part. Okay. I have few
Ma'am, I
more.
have a doubt.
Yes, ma'am.
Ma'am, what's the point of calculating the E cell because we didn't use it anywhere?
We didn't use it. Yeah. Even while I was explaining the Nernst equation, even I was thinking, but they have given all the values. I think I have done a continuation of numerical. I have done a continuation of this numerical with this one. I guess, Arya, see, find the RP and OP of CR by CR3 plus FE2 plus and FE I have given, right? So I think I might have done a continuation. So for many numerical, no, I have used one equation to get E naught or E of, like that, I think. But here to find EMF of cell, we have not used E of cell anywhere. That's where we found out, right? E of cell is to be found out. That has to be found out in the numerical. It was the one which I found was 0.26, right? What was the answer which I got? That is also 0.26 only. That's also 0.26 only.
Ma'am, so does the answer remain same every time?
No, 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 no. This is a continuation of this one. See here also they have given Cr3 plus value as 0.1, and it is Fe2 plus by FeCr3. Many numerical, no, I have made like two problems same with the same equation. Only the criteria will be different. I might have asked E naught, E, like that. But here though your question is very reasonable because we have to find what is E of cell, right? So we have to find out what is E of cell. But here directly all the four values were given here. I think I got this two from the previous question. Fe2 plus by Fe and Cr3 plus Cr. From the previous numerical I have taken these two values. Okay, Arya?
Yes, ma'am.
Generally you will be given only E naught values. E naught of cell values will be given. Say for example, E naught of chromium and E naught of iron should be given. This should not be given because if this two is given, then there is no point in dealing with Nernst equation, right? Yes, no, ma? If
Yes,
this
ma'am.
is, yeah, if this is known, since E of Fe, E of Cr3 was given, so we have directly solved what is E of cell, that is 0.26, right? Then we went a long way using Nernst equation to find that, provided the answer was 0.26, our intention is to find the E of cell at different concentration and different temperature, right? That's why we went a long way. But here, though, these four values should not be given. Only two values will be given. Only E naught value will be given. You have to find out E of cell. Okay, Arya.
Yes, ma'am.
Because the main what is that, the main function of Nernst equation is to find the E of cell at any concentration at any temperature. Yes, no ma. So this two values was from the previous numerical. This was from the previous numerical, we have used it. Okay ma.
Okay, ma'am.
0.75. Yes ma, from the previous sum, see minus 0.75 and 0.59 from the previous problem I have written here, and I have used it to find this one. Okay. So you can take this, the entire PDF I'm going to share it in the group, so you can try other two numericals also ma. Okay, we I have, I think I have one or two here and all. No, it is very light, so 1 2 3 will be very very light, 3 4 pages. So you just see the numerical, you just see the heading, and then you can solve by yourself. Okay ma. So after that, about SHE, we have to learn She, standard hydrogen electrode, we have to study. When that is done, then we are 75% crossed the chapter. We have this metal activity series. After metal activity series, when we are entering conductance, then we can breathe slowly. From there, it is easy only. Okay, ma? Okay, one
Ma'am,
minute.
tomorrow will we be continuing the chapter or revision?
Tomorrow we will continue, because so many days I have been doing revision, right? We are starting. Wait a minute. Let me stop recording.